Welcome to Algorush. Think about the last time you searched for a photo on your phone or looked up a contact in your address book. It was basically instant, right? So how does a system sift through maybe millions or even billions of items to find the one you want in just a blink of an eye? Well, the answer is this really elegant and powerful data structure, the B tree. And today we're going to pull back the curtain and see exactly how this unseen engine makes our modern digital world tick. But before we can really appreciate just how clever the B tree is, we have to understand the problem it was built to solve. And trust me, it's a big one. It all comes down to the absolutely massive difference in speed between a computer's main memory and its physical storage. I mean, really, how is that possible? A computer isn't just scanning every single item one by one. That would literally take forever. The secret, it turns out, is a clever design that gets around a fundamental physical bottleneck in how computers actually store and retrieve information. Okay, so here's the heart of the problem. Getting data from your main memory, your RAM, is like flipping a light switch. It's electronic, it's insanely fast. But getting data from a spinning hard disk, that's more like having a robotic arm try to find one specific word in a giant library. The slowest part isn't even reading the word. It's the time the arm takes just to move to the right book and open it to the right page. In computing, that physical movement is called seek time, and it is an eternity. It's the real villain of our story. This massive speed gap creates a huge problem for data structures that we'd normally use. A classic binary search tree, which is amazing in fast memory, becomes a total performance nightmare on a slow disk. See, it's tall and skinny. To find anything, you might have to jump from node to node to node, going deeper and deeper. And each one of those jumps could mean another painfully slow disk seek. For a billion items, that tree is going to be incredibly deep, requiring dozens of these seeks. It's not going to work. So this calls for a totally different way of thinking. We need a data structure that's engineered from the ground up to minimize those agonizingly slow disk seeks. One that's designed for the physical reality of a mechanical disk, not the ideal world of instant access memory. And the solution is to just flip the whole design on its head. Instead of being tall and skinny, we build something that's short and wide. And that is the B tree. It's a data structure that's designed to work with the slowness of disks, not fight against it. Its entire reason for existing is to be incredibly flat, to minimize those trips to the disk. So how does it pull this off? How does it get so flat? Well, it starts by thinking in bigger chunks. Instead of fetching one tiny piece of data at a time, it works with pages, these fixed-sized blocks of data. The idea is, since going to the disk is so slow and expensive, every time you go, you might as well grab a whole box full of useful information, not just one little piece. You want to minimize your trips, right? All right, so let's pop the hood and take a look inside this thing. The B tree's simple, layered hierarchy is really the secret sauce to its speed. The structure is actually pretty straightforward. Right at the very top, you have one single root node. That's your front door. Below that, you can have one or more levels of what we call internal nodes, and then all the way at the bottom, you have the leaf nodes. That's it, root, internal nodes, and leaf nodes. Now, this next part is absolutely critical to understand. Those internal nodes, the ones in the middle, they don't actually hold the data you're looking for. Not at all. Think of them as just a series of highway signs. They hold separator keys that basically just point the way. You look at your search key, you compare it to the signposts, and they tell you which road to take to get to the next level down. So you follow these signposts down through the tree, and eventually you get to your destination, a leaf node. This is where the treasure is. The leaf nodes are the only place where the actual data records are stored. And importantly, all the leaf nodes are at the same exact level, which keeps the whole tree perfectly balanced. Okay, so we have the map. Now let's actually trace the path to find one specific piece of data and see why this whole design is just so fast. The whole process is really direct and really fast. First, the system does one slow disk read to grab the root node. It compares your search key to the signposts on that page, which tells it which child page to go to next. Then, it does another disk read to grab that child page and repeats the process. You just follow this path of signposts down until you finally read a leaf node page. And since that page is now loaded into fast memory, you can scan it super quickly to find the exact record you need. And here is the big payoff. Because each page, each node, can point to hundreds or even thousands of other pages, the tree is just incredibly shallow. And the result is kind of mind-blowing. To find one single record among billions, a system often only needs to do 3 to 5 of those slow disk reads. That's it. That is the revolutionary power of this short and wide design. But of course, the innovation didn't stop there. Modern systems use an even cleverer refinement of this idea that manages to squeeze out even more performance. And this is the B+ tree. Its key innovation is brilliant and simple. Only the leaf nodes, the ones at the very bottom, hold the actual data values. The internal signpost nodes hold only the keys they need to navigate. So by stripping all that extra data out of the internal nodes, they become way smaller. This means you can pack a lot more of those signpost keys into every single page you read from disk, which in turn makes the tree even wider and even flatter. It's a fantastic optimization. So look, this isn't just some abstract concept from a computer science class. The B tree and its variants are the real-world engines that power the technology we all depend on every single day. You will find these things absolutely everywhere. They are the core indexing structure in pretty much every relational database you've ever heard of. They're also deep inside many of the most popular NoSQL databases. And get this, even the file system on your computer uses a B-tree-like structure to keep track of where all your files are. They are truly the foundation of so much. This really says it all. Without this elegant solution to that fundamental disk speed problem, the fast, data-heavy ops we just take for granted, they simply couldn't exist. B-trees are the quiet, reliable workhorses just doing all the heavy lifting behind the scenes. You know, the B-tree is just this perfect example of a brilliant solution that was tailored to a very specific, very real physical problem. It kind of makes you wonder, right? What other invisible algorithms and data structures are out there quietly shaping our digital reality? What other unseen